Hello there, Mr. Sutton here, bringing you the Algebra 2 4.1 lesson on graphing polynomial functions. This will be a two-parter. Throughout this one, we will be identifying and classifying polynomials and evaluating them at certain x values. In addition, in order to graph them, we're going to determine the end behavior, and we'll use a table to graph the polynomials. And for the honors portion of this lesson, we'll also be figuring out the average rate of change, or AROC, for a polynomial function. Before we dig too deep into polynomials, let's make sure we have a common understanding of some key terms and definitions that we'll be using throughout this lesson. We should start by defining what a polynomial is. That's a pretty important one because that's what this entire chapter is about. So a polynomial is a sum of power terms with only whole number powers. And there's a lot in this one statement, so let's break it down a bit. First off, it's a sum, or it could be a difference. It could be either one of those, plus or minus, but we're adding a bunch of power terms together. We're not multiplying them. It's not factored out or anything like that. We've also got power terms. Those are terms that have maybe x to some exponent. That's what we're talking about. And the exponent has to be a whole number. So it could be 0, 1, 2, 3, 4, those sorts of numbers. It can't be negative. It can't be a fractional thing like radical sorts of functions. It also couldn't be a variable like an exponential function would have something to the x power. Can't have any of that. So with that in mind, polynomials, we can talk about a lead term. And when we say lead term, we're talking about the term with the highest power. Now this may also be the term that is the first term in the polynomial, but it doesn't have to be. It could be out of order and hidden somewhere in the polynomial. When we talk about the degree of a polynomial, we're talking about the power of the lead term. That is the degree. So if my highest exponent was 7, that would be a 7th degree polynomial. Now it is a good idea to have your polynomials in a certain order to make them easier to read. That is called standard form of polynomials, and this is when you have a decreasing order of exponents, so that your first term is also your lead term and the other exponents go down in order. So we're going to go through and actually give some examples of polynomials and also give some special names. There's two ways of classifying polynomials. One is by their degree and one is by the number of terms in the polynomial. We'll look at the degree first. So I've got this little table here that has examples of all the polynomials from degrees 0 through 4. And we could go higher, but we don't really need to go higher than 4 for our purposes here. So we'll do an example, and then we'll talk about the special name of that because this name is also going to be used quite frequently. So if you have a 0 degree polynomial, for example, something like 7 times x to the 0 power. Well, since anything to the 0 power is just 1, this is really just 7 times 1, or 7. So that is actually just a constant. Believe it or not, a constant is considered a polynomial. So when you were learning to count 1, 2, 3, 4, 5, you were actually using polynomials your whole life without even knowing it. So that's kind of neat. Now the next one up, the first power, first degree, that would be like 3x to the first, or just 3x, because we don't have to write an exponent of 1. You might recognize this from a few chapters ago when we were doing a little bit with lines. This is a linear polynomial. And we could have another term along with this. We could have like 3x plus 7, have something in mx plus b form, and that's okay. When we talk about a degree again, we're just talking about the highest exponent. We don't really care about any of the other exponents, which is demonstrated by this next example for a second degree polynomial of x squared plus 4x minus 1. What makes this second degree is this highest exponent of 2. Now we did a whole chapter on these very recently. You might remember these were called the quadratic polynomials. And you might wonder, well, why quad if this is a 2 and not a 4? Well, this is also called squaring something, and quad and square go together. So that's where that connection is. Now if we go up to the third degree, third power, like this one here, this is called a cubic function, because this is really x cubed is how we pronounce that. And then if you do fourth power, like 2x to the fourth plus whatever, this is quartic. So there's your fourth power. And you could go higher than fourth. There's a fifth degree that they sometimes call a quintic function. Higher than that, I don't think there's any special names. They just call it like whatever degree it is, like a sixth degree polynomial or whatever. So this is naming things with degrees. Now you could also talk about specific terms of a polynomial and give it these names. For example, this 8x term in this quartic polynomial, you could call this 8x the linear term. Now moving forward a little bit, we can also classify polynomials by the number of terms in the polynomial. So for example, if we have one term in a polynomial, like this 3x we talked about recently, that is also called a monomial. It's still a polynomial, but it's a special type of one. And then if we have two terms like this 2x to the fourth plus 8x, we can call that a binomial, bi for 2. And then, of course, this three-termer here that was a quadratic, we can call that a trinomial. If we want to get really fancy, we can combine these two names to be specific about what we're talking about. For example, this expression in here, we could call this a quadratic trinomial. We could call this one, this 2x to the fourth one, a quartic binomial, and so on and so forth. Now that we've established that theoretical background on polynomials, let's see if we can apply it here. So for the next two examples, we're going to determine if the function given is a polynomial. And if it is, and only if it is, then we'll write it in standard form, state its degree, the type, and based on degree, not number of terms, and also the leading coefficient. So here's the g of x function. If you're feeling confident, then pause the video and see if you can answer all this stuff for g. All right, let's see how it went. So taking a look at whether or not this is a polynomial, we just look at the exponents on the terms. So we have a 3, a 4, and this is an invisible x to the 0 here. Those are all whole numbers. Since all the powers are whole numbers, that means that g is a polynomial. Since it is, we're going to go ahead and write it in standard form. So in order to do that, we basically just need to put it in decreasing order of exponents. The highest exponent is this x to the fourth here. So we're going to start this with radical 2x to the fourth when we rewrite it. And then this negative 0.8x cubed is the next one. And after that, the minus 12. Now, it's a good idea to put things in standard form before you figure out all this other stuff, because a lot of it's based on the lead term, and it's nice if the lead term is also the first term. Remember, those aren't necessarily the same thing. The lead term for the original g of x function was still radical 2x to the fourth. It was just out of order. So now looking at our lead term for the degree, that's just the exponent for the lead term. That's a 4, so that's a fourth degree. The type is based off the degree. Fourth power, remember from our chart, was quartic. And then the lead coefficient is just going to be this radical 2 that's multiplied by the lead variable here. So radical 2 is our lead coefficient. So hopefully that first example went well for you. Here's another one to try yourself on, the h of x function. Pause the video and see what you can do with this one. All right, so looking at our exponents, we've got a negative 1, we've got an x, and the square root, that's going to be the 1/2 power. And all of those, negative 1, x, and 1/2, none of these are whole number exponents. So for that reason, it turns out h of x is not a polynomial at all. And we're not going to bother putting it in standard form or any of these other things. And not really sure, how you even compare like x and negative 1 and things like that. Now, it is worth noting that this x squared is okay. However, it just takes one bad apple to spoil the bunch, and we've got 3 here, not just 1. For our next example, we're just going to be evaluating this f of x polynomial given the value x equals 3. Basically, all this involves is just plugging 3 in for all the x's and then using PEMDAS to sort it out. So pause the video and let's see what you get. All right, so plugging 3 into all of these. Now, we could probably do this without a calculator. In fact, let's do that first and then we'll check our answer with a calculator. So PEMDAS, exponents happen before multiplying, which then happens before adding and subtracting. 3 to the fourth is 81. 2 times that is going to be 162. And then 3 squared is 9, times 8 is 72, and we're subtracting that. And then we have 5 times 3, which is 15, and the minus 7 doesn't change. 162 minus 72, just going from left to right here, that's going to be 90. Plus 15 is 105. And then subtract 7, that should give us 98. Now we can use Desmos to plug things into the calculator. So here is Desmos, and if you want to use it for this purpose, you just have to define the function in Desmos. So f of x equals 2x to the fourth minus 8x squared plus 5x minus 7. And then you can plug anything you want into that function now that you've defined it. So we wanted to do f of 3. Let's see what that looks like. F of 3. And it comes out to 98, just like we got doing it by hand. Before we can really do the graphs justice, we need to introduce a concept called end behavior. Now this seems kind of silly with an infinite function like polynomials that go forever to the left and the right. There really is no end in terms of x or really y values, but it helps to kind of think about where is the graph going as we go towards the far left or the far right. So the concept of end behavior is talking specifically about what your graph is doing in terms of y values as x approaches both negative and positive infinity, far left and far right behavior. So to figure out what this end behavior kind of looks like, we're going to do a little experiment. This would be a good time for you to go to Desmos, the graphing part of it, and hey, graph some polynomials. While you're doing this, pay attention to what happens specifically when you change the sign of the lead term, and then try changing the even or oddness of the exponent in that lead term. And then, how about when you add more terms with lower powers after that? So there's really kind of three things to test out. Pause the video, play around with it, and then you can watch me play around with it for a bit, and then we'll come together with some conclusions. All right, here's our good friend Desmos. Let's graph a polynomial. So we'll just do f of x equals, let's do x to the third power. Why not? X to the third. All right, so there's x to the third. Now, what happens if I change the sign of this thing? Let's see, so I put a negative out in front. Oh, and it reflects it vertically, which we knew that was going to happen because we've done transformations before. But that also changes the end behavior. Positive with x to the third, we were going from negative infinity down here to positive infinity up here. If we make it negative, now that changes everything. Whatever was going to positive is now going to negative infinity and vice versa. Now let's see what happens if we make the exponent even. So there's fourth power. And if we make that negative, that reflects that one as well. So we've got like four basic shapes now. We have negative and positive even power, and then we have negative and positive for the odd power. Now what happens if I make this a higher odd number like 5? Well, it turns out that doesn't actually change a whole lot. The end behavior still stays the same. And if I make this a 6, now we have another kind of parabola sort of shape like we had with x to the 4th. How about x to the 8th? Well, not very different. How about x to the 20th? It's kind of getting squared off more, but it's still the same behavior. And if we do x to the 21st, we've got like the x to the 3rd behavior kind of repeating. Now what happens if we add a few more things in there? Let's add a x to the, x to the 10th. Let's add something even in there. So it changes a little bit of this stuff happening toward the middle, but the end behavior is unaffected. And if we add some more terms, maybe like a minus 80 x to the 9th, why not? And the end behavior really has not altered at all. And if we add a little constant in here, I mean, that shifts things a little bit, but our end behavior is still, if we zoom out, negative and positive infinity. So here are some conclusions we can draw about all of that. The polynomial end behavior is going to be determined by the sign of the lead coefficient. Those other coefficients didn't really affect the end behavior. So the sign of the lead coefficient and whether the degree is even or odd. And it turns out you can play around as much as you want, but these are the only two things that are impacting the end behavior: the sign of the lead coefficient and the degree, even or oddness. Now to kind of sum up what we found by experimenting, I made a little chart here that you can fill in on your guided notes. We got two directions going. Across here we've got the degree, whether our polynomial's lead term has an even or odd exponent, so odd or even will do. And then we also have the lead coefficient sign, positive or negative. So we saw the positive odd degree ones ended up going from down to up. It was kind of a line sort of pattern here. And when they were even, it looked sort of like an upwards parabola. So this was even, positive. Now, if we had an odd function that was negative, that was a line sort of shape but going down instead of up. And then negative even, negative x to an even power, gave us an upside down parabola. And it turns out these are the only 4 end behaviors that you're going to see with polynomials. So now that we've played around a little bit with end behavior, pause the video and see if you can figure out the end behavior of this function. Specifically, as x approaches negative and then positive infinity, what is happening to f of x? What is happening to the y values? Alright, so when we do this, we don't actually need to graph anything on Desmos. We can just focus on this lead term, and we'll make sure that this is the highest exponent. It is. X to the 4th is higher than anything else, but you should always double check. Sometimes they like to hide the higher terms in the function in between things. So focusing on that lead term, since this is negative x to an even power in terms of the overall picture here, that means this is going to be one of those upside down parabola sorts of shapes. Again, there might be some differences kind of in between the ends, but on the ends you're going down and down. So then as x approaches negative infinity, as we move to the far left, we're going down forever. So we can say that f of x is approaching negative infinity. That's what down forever looks like when you put it on the f function. And as x approaches positive infinity, as we go forever to the right, f of x is, well, it's still going down. Everything is down here. So negative infinity in that direction as well. So at this point, we're going to graph a polynomial ourselves. We're going to pull it all together. End behavior is going to be used, and we're also going to use what we've learned about evaluating polynomial functions at specific values to help us out here. So our idea here, our process, is we're going to use a table of values along with end behavior to get a rough sketch of this polynomial. It won't be totally accurate, but it'll be enough for at this point in our education. So specifically, when we make a table of values, we're going to plug in x equals -2 through +2, all the integers there, and that'll give us 5 points. So making our table, we're going to plug in -2, -1, 0, 1, and 2. So I'm going to do this on Desmos, and I'm going to use the scientific calculator to do all of this. I could use the graphing one, but then if I'm allowed to use the table in the graphing part of it, well, I might as well just plug this function into the graphing part and get the graph that way, right? This is if you don't have the graphing utility totally available to you. So here's my Desmos scientific calculator, and let me just put my function in here so I can quickly plug in values. So we have -x to the 3rd plus x squared plus 3x minus 3. And I'll go down and start entering things in. So we've got f of -2 to quickly evaluate this at -2, and that gives us 3. So there's 3. Feel free to pause the video if you want and get the rest of them. All right, so let's see here. Plugging in -1, we got -4. Plugging in 0, you don't really need a calculator. That's going to zero out all these x terms and give you -3. Plugging in 1, you probably don't need a calculator, but just to be on the safe side with those negatives, oh, that actually comes out to 0. That's kind of nifty. And then plugging in 2, f of 2 gives us -1. All right, -1. So we're going to graph all these points now. We've got -2, 3. And one thing it's good to do before you actually make your grid is just look at the y values. These y values don't look too crazy, but if you had something like -40 or 100, you'd want to change your grid lines to accommodate that. So now we've got -1, -4, that's down here. 0, -3 is right here. And then we have 1, 0, and 2, -1. So one other crucial element to this, I could connect these dots and get something, but I don't really know what's happening to the left of my first dot and to the right of my last one here. And I mean, I could keep making more and more x values, but that's not necessarily going to tell me where this thing goes as x approaches negative infinity or positive infinity. To do that, I need to look at the end behavior. So your next step is going to be to use the end behavior, again, using that lead term, to determine if your graph is going up or down forever before the first point and after the last point. So with that in mind, pause the video and see if you can use end behavior to figure that out, and then get the rest of the graph here. All right, so taking a look at my lead term, we have a negative x to an odd power. That means I'm going to have a down line sort of end behavior, where I'm starting up here and ending down here. So graphing all that out, we're up here now, coming down from positive infinity, and we are going through all our points, and then going down forever, because we said we're ending at negative infinity for the function values. So this is a rough graph, very rough. I don't know a whole lot about this polynomial other than that it goes through these points and has this end behavior. I don't know what the exact other x-intercepts might be here. I do know the y-intercept, but that's because I plugged in 0 specifically. One thing I also don't know is exactly where this thing turns around. It might have gone down further before turning around and coming back through this point. It might do a bunch of kind of squiggles before it gets there. I don't really know any of that. There's ways of figuring that out that we're going to see later on, but for now we're going to have to be content with what we've got. All right, now that we've graphed out one of those polynomials, pause the video, and here's just another one, same kind of problem. See if you can get this one. All right, so just like before, we're going to do our table from -2 to +2, and we're going to go to Desmos and get some function values out of that. So let me plug in my f of x function to Desmos. So we have x to the 4th minus x to the 3rd minus 4x squared plus 4. Plugging in -2, that gives us 12. And then let me just quickly get my other values. So we've got 2, 4, 0, and -4. 2, 4, 0, and -4. Nice how you can just quickly plug that in without putting it in like 3 different spots every time. All right, graphing those now. Now since I go up to 12 here, notice that my grid lines, I left enough space to go up to 12. So just kind of plan ahead when you make your grid and do your axes. So we have -2, comma 12 up here. -1, comma 2, 0, comma 4 is right there, and we have 1, 0, and 2, comma -4. For my end behavior, my lead term is a positive x to an even power. So that means I have an up parabola sort of shape to this thing, which means that I'm starting high up here, and I'm also going to end going up. So we're starting up here, coming down through our other points, and then ending all the way up here. So if you've been doing this lesson for the non-honors college prep course, then you can actually stop right here. This is the end of that course's version of this lesson. Feel free to turn off the video and do whatever homework you need to do. If you're doing the honors version of the course, then we're going to keep going and do an application problem. So stay tuned for that. All right, so if you're doing the honors course, thanks for joining us for this one last application problem. Say hello to our good friend, the African wild dog, one of the most endangered carnivores on Earth, apparently. I don't know how something so cute could be endangered, but there you have it. The estimated population of these critters under human care is modeled by this polynomial function, where t is the number of years after 2000. So let's just stop right there before we do any problems. So you might be wondering, where do they come up with functions like this? And that's a fair question. This is actually one of the biggest applications of polynomials. Not specifically, modeling wild dog populations, but really modeling any function, any kind of real life function that goes all over the place and doesn't really follow a strict linear or quadratic pattern. Polynomials, depending on what your exponents are, what your coefficients are, they can take any number of twists and turns that you want them to. They're called chameleon functions, in fact. So this is a huge application of these. So with that in mind, let's use technology, which is usually what we end up doing with these real-life problems, because the reality is a lot messier than the neat, clean problems you normally get in a math class. Let's use technology to graph this thing on the interval from 1 to 18, and then we're going to just describe the behavior of the graph, whether it's increasing or decreasing on various intervals. So pause the video, check out Desmos Grapher for this thing, and see if you can get that to go for you. Alright, so let me show you how I did this. Let me go to Desmos here. So I'm going to enter my function in there. Let me just see the function. So we've got p of t equals 0.368t cubed minus 11.45 t squared, and then plus 109.5 t plus 286. So there's a small piece of my function, but not really enough to see what's going on. Now they said they wanted to model this thing from t equals 1 to 18. So let me go to my window, and I'm going to adjust this. Instead of going from 1 to 18, I want to leave myself a little bit of room on the left and the right. So I'm going to go from -1 to +20. That should give me a pretty decent window on what's going on. Now for the y values, if we just go back to our screen here, we can't really see any of our graph with the current y values. And that's probably because there's way more African wild dogs, even if they're endangered, than just 10. So let's go back to window, and let's adjust my y-axis. I don't know how many wild dogs there are. I could plug in some values to get a rough number, but let me just put in 100 for my upper y value. And then going back, I see that that's not showing me anything. So let me try something else. Let's go up to 1,000. Just keep multiplying by 10. Eventually I'll get there. Now it looks like that actually shows our graph pretty well. You know, there's sort of this middle range of 600 wild dogs, and then it increases after that. So now they were asking basically where's this thing increasing and decreasing. And we're going to be turning around at various spots. If you click on the function and then look at these little gray dots, these are giving you local maxes and mins. And if you click on these, it'll make the value stay there so you don't have to keep hovering over it. So here's my other one down here. So in terms of places where this is increasing, it looks like we're increasing from time equals 1, so 2001, until roughly, I guess this is 2007. And it also happens to be increasing from 2013 to 2018. So I'm going to put that down, increasing from 2001 to 2007 and from 2013 to 18. And it looks like if we just go back there, we are decreasing on this interval from 2007 to 2013. So we'll put that in there as well. So we're going to go to the next part of our example now. We're still having fun with the African wild dogs there, but now we're going to be asking what is the average rate of change, which is another word for basically slope, in the number of dogs from 2001 to 2018. So the average rate of change, it's important that they're asking for the average rate of change and not just the rate of change, because if you look at this function that we graphed on the past part of this problem, the rate of change is kind of changing. The slope of this thing is not just a constant flat line sort of slope. So what we have to figure out instead is the average rate of change. And the way we're basically doing that is we're looking at the slope of a line from 1 to 18. If we were to draw a line connecting those spots, what would the slope of that line be? That's what we're really asking about on this next question. So one thing that might be useful to remember is the formula for slope, which I'm going to make the more general formula for average rate of change. So here's our AROC formula, average rate of change. So we've got f of x2 minus f of x1. That's basically y2 minus y1 over x2 minus x1. This is just your slope formula, souped up a little bit to call the y values f of x values. So with this in mind, see if you can find the average rate of change of this function from 1 to 18. All right, let's see how that went. We're going to do this on Desmos. So what I'm going to be doing on Desmos, I'm going to need to do basically p of 18 minus p of 1 all over 18 minus 1. Because the f of x values are really p of t values, and the x values are really just t values in the context of this problem. So if I plug that in Desmos, so here I am in Desmos. Now I already put the p function as an entry here. There was our p function. So I can just use that now by plugging things into it. So let me do p of 18, which is about 693.4 and some change there. P of 1 is 384 and some change. So let me basically just do, let's see, fraction. We'll do this value. Let me just cut and paste that. Minus this value, cut and paste, all over 18 minus 1. And that comes out to about 18.174. So there was the things I ended up plugging in, and I could have really just done p of 18 minus p of 1 like I had written here. I just wanted to show you the values there. But that all came out to 18.174, and this is going to be dogs per year for our units. T was in years, P was in number of dogs, so there it is. For the last part of this problem, we're asking, do you think this model can be used for years after 2018? And explain your reasoning. So pause the video and write down a few thoughts. Alright, so to see if this model can be used after 2018, let me go back to my graph and let me just start, seeing what happens if I zoom out a bit. So if we keep going, we're getting some pretty crazy values, right? Like in 2030 there's 3,000, and I mean if we go even further, now there's like in 2040 there's almost 10,000 of these things. So this isn't very realistic as a model for going too far after 2018. The problem is, since this is an odd polynomial, since it's a polynomial in general, this thing is going to increase without bound as your time grows. So eventually you're going to get more and more unrealistically high values for your number of dogs. And all polynomials kind of have this flaw where they eventually go to infinity. So at some point you have to kind of set some boundaries for where your model applies. So that's it for this one. Hopefully, unlike the population of the African wild dogs, your knowledge continues to grow without bounds. Till next time, Mr. Sutton signing off.